Hi there. Thanks for joining us. This is Space Nuts, where we talk astronomy and space science and sometimes puppy dogs. Who knows? My name is Andrew Dunkley, your host. It's great to have your company. Coming up on this episode, we are going to look into a discovery made through the Perseverance rover on Mars. Have they found what could have been life in Mars's history, or is it another rock that's just got a stain on it? Also, we've got some news on the Hubble tension, and the Large Hadron Collider is no more. Well, it's going to be more, but it needs to be no more to be more. We'll tell you all about it on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Joining us again to discuss all of those things and more is Professor Fred Watson, astronomer at large. Hi, Fred.
Hello, Andrew. Good to see you.
Good to see you too.
Good to be back on Space Nuts.
It is. It's very good. We've got a lot to talk about, so we might as well dive right in because it wasn't so long ago that we had a bit of a chat about a rock that they found that they said came from Mars, and it showed there was life, and then it turned out to be nothing like that. And now we have a story popping up that suggests the Perseverance rover may have detected complex carbon molecules in Martian rocks that may have been signatures for life. You can't say, look, they found former life on Mars. It's all over, Red Rover. Boom, boom. That's a good joke. Think about it. And
I didn't need to think too hard.
And look, you just got to take this with a grain of Martian salt and hope that that's what they've actually found. That's what it's all about.
You have to go back to that pink planet we were talking about a few episodes ago to get the grain of salt.
The pink salt planet.
Yeah. Indeed. So, yes, the story is, as you've hinted, a kind of extension of a story that we covered a few weeks ago, which was this particular rock, which is from an outcrop called the Bright Angel outcrop on Mars. So this is the Perseverance rover, which you'll remember is working hard in Jezero Crater, where there is a river delta from probably 3.5 billion years ago. So the Bright Angel outcrop, and the particular rock that they found, I can't see whether it had a particular name, but it was a mudstone rock, which had basically, as you said, stains on them, stains on the surface. Stains on Mars will be interesting because you'd wonder where they came from. But it's got surface spots and what have been called nodules. And the reason why it caused excitement was that some of those features superficially resemble the features that are produced on Earth by fossilized microbes. And that's what we covered actually back in 2024. It seems like only yesterday. Yeah. But we did talk about that. Or maybe, no, it was probably last year, actually. I think that's when the results came out. So last year, 2025. Yeah. And a quote. There's a nice Guardian piece on this story, but there's a quote from Sean Duffy, who used to be the acting head of NASA, who said of that discovery, "This very well could be the clearest sign of life that we've ever found on Mars," which is an interesting comment. And of course, all astrobiologists and all scientists probably and all podcast presenters couch this sort of discovery in very, very broad terms because this is certainly not a definitive discovery of life on Mars, but it has basically gone further in the sense that the samples that Perseverance took from this mudstone showed that there was something called macromolecular carbon on its surface. And that's it's carbon compounds. Probably. Excuse me. Sorry about that, Andrew. Just bellowing into my microphone here. I do apologise. It's probably several organic molecules or types of organic molecule, and of course, organic means containing carbon, associated with life normally. But the analysis of this shows, and the analysis by Perseverance shows that it is a possibility that this life, these macromolecules, carbon macromolecules, could have been the result of life processes, but they could also come from basically, essentially geological processes, tectonic processes. And so that's where the thing stands at the moment. We know from work that's already been done by the Perseverance rover. And Perseverance, so Curiosity went to Mars to determine whether Mars was ever habitable. And we know that from Curiosity. It found that out within the first 2 weeks of being there. But we know now from Perseverance that Jezero crater was also a habitable environment, at least for some sort of primitive level of life.
Yeah.
But of course, the issue is that we won't be able to do the proper tests on these samples until we get these samples back to Earth laboratories, where there's far more refined equipment than you can carry on a little rover on Mars. And the problem is we don't currently have any way of doing that, of getting these samples back, because the mission to do that, a joint NASA European Space Agency mission, fell foul of politics in the United States and was cancelled earlier in the year. We knew it was in trouble anyway because the cost had sort of blown out. So it's not a surprise that happened. But at the moment, there's nothing on the books to get them back. Few plans going on, I think, but not to get them back.
Yeah, and that's frustrating. But I suppose in the scheme of things, we all want to know whether or not Mars had life, but it's probably not one of the most urgent things to deal with. We'll get around to it. And chances are that those cylinders, I think they are, that the deposits are in, will be collected as a part of another major mission. That would be my thinking, sometime in the future.
You're probably right, although it's a very specific type of mission that's going to go and collect these samples and then send them back to Earth. That's the tricky bit.
It is.
You've got to. It's probably a two-step process where you've got an orbiter sent to Mars, goes into orbit around Mars. That drops a probe onto the surface. The probe picks up the cache samples, not CaSH but CaChe, and brings them back up to the orbiter, and then the orbiter sends off a probe to the Earth, and that re-enters. It's a very complex process, which is why the cost blew out. But I do have my own view on what might prompt some urgency with this, and that is that the Chinese are planning to do a sample return mission to Mars in the 2030s.
Right. So
if anything's going to stimulate some action on this, my guess is that that's what it would be. And all praise to the China National Space Agency for aiming high. It's a great thing to do.
It is. And the other interesting thing, I suppose, and you mentioned Curiosity, it's starting to build up evidence that the potential for life on Mars was widespread across the planet's surface.
Yes, correct. That's right. I meant to mention that. That's absolutely right. That when you've got mudstones separated by 3,000 kilometres or thereabouts, and giving you the same sort of answer. Yeah, that I think is it's a very, very strong evidence for there having been the possibility of life on Mars, and that it might be findable, if I can put it that way. If the conditions are suitable for life everywhere, then there might be remnants of living organisms everywhere on Mars, which we have a good chance of finding. Because when NASA and other space agencies aim to send spacecraft to Mars, it's not quite just a tail on the donkey thing where you just poke it in willy-nilly. You've got really good reasons for going to any specific place, and certainly Jezero Crater, it was a masterstroke sending it to a lake that had a river delta in it.
Yeah, they picked a good target. That was intentional, and
that's right.
It seems to be paying off. Fingers crossed. But too early to tell. But looking somewhat promising is, I think, the best way to describe it at the moment.
That's right. It's not a kind of negative result. It's not saying, "Oh no, there's no life on Mars." It's saying, "There might be. It might have been.
might have been, and still might be."
But still might be. That's right. Yeah, exactly.
You can read all about that at theguardian.com, or you can read the paper that's been published in Science Advances. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Space Nuts.
Now, one of our semi-regular topics is the Hubble tension, and it's back in the news again because of another detection involving the collision of neutron stars. Is that right?
That's correct, yes. Yes, so the Hubble tension is one of these irritating things that just won't go away.
Well, it's being described as one of the biggest challenges in modern cosmology. So, yes, it won't go away.
It won't go away. But it's not. It's a bit weird. I did a radio segment about it with an Australian commercial radio station yesterday morning because of the headline story.
Yeah.
And I thought, how do you make this exciting? It was first thing, it was a breakfast show, and the guys who were interviewing me were clearly not impressed with it. Normally I get lots of questions from them, but
it may well have just been something that goes into the too hard basket, because it's not an easy thing to get your head around.
It's not, that's right, it's not. There's a lot of gobbledygook attached to it. Anyway, let's have a go. We have a very erudite audience on Space Nuts, and Space Nuts listeners will probably already be aware of all this anyway. But yes, so what's the Hubble tension? We have two measurements of the Hubble constant, which is the number that defines how fast the universe is expanding now. Yeah. It's the expansion time or the expansion rate that we are seeing. As you and I have said many times before, it's measured in units of kilometers per second per megaparsec. And a megaparsec is 3.26 million light years. It's the units astronomers use because you can't measure light years, but you can measure parsecs. So that number is the magic number. And we have two different ways of determining it, both of which now have achieved a really high level of precision. There was a talk that I was at a couple of months ago in Germany where one of the experts was talking about this, and the sort of uncertainty limits that are put on each of these two different methods of determining the Hubble constant, they were very small, on the order of 1 kilometer per second, very, very accurate measurements. But they disagree. So you can do it two ways. The first way is to look at the cosmic microwave background radiation, the good old background glow of the Big Bang that is everywhere in the sky. It has undulations on it in temperature, which we recognize as being differences in the temperature of the Big Bang fireball, which are caused by acoustic oscillations. It's the bang of the Big Bang. Mm. But you can use those undulations to get a measurement of the Hubble constant. And the value that technology gets, or that method gets, is 67 to 68 kilometers per second per megaparsec. The other way of measuring this is to look in the nearby universe. You look at galaxies whose distances are measured in millions or hundreds of millions of light years, and that's very local compared with the 13.8 billion light years of the cosmic microwave background. So you look locally, and you look for the traditional methods of finding the distances to galaxies, which one of them is by what we call Cepheid variable stars. That was the way that galaxies were first established to be a long way off in 1923. You can also do it with supernova explosions. All of that sort of stuff gives you another alternative value on the Hubble constant. And that gives you a higher answer. So the local universe gives you an answer of about 73 kilometers per second per megaparsec. So that's roughly 5 kilometers per second per megaparsec higher than the one you get from the Hubble constant. Now that's, I suppose that's something like a 6 or 7% difference between them. And I can tell you 30 years ago, when I was an astronomer kind of a bit more directly connected with all this, 5%, we'd die for 5%. That was, or 6 or 7% or whatever the difference is, 5 kilometers per second per megaparsec, because most of them differ by 50 kilometers per second per megaparsec back then. And it was the Hubble telescope that actually nailed it down to be in the region of 70. But yes, we have this discrepancy. What's the answer? So actually, I might just quote, there's a very nice conversation piece by one of the astronomers involved with this, who is a radio astronomer at CSIRO, the Australia's National Science Agency, Kelly Gorgie. And let me see if I can find this comment. Yes, that's that. So that Kelly says that this is the Hubble tension. What does it mean? Could it be something has gone awry in one or both methods? Despite intense scrutiny, nobody has found any mistakes. Alternatively, our understanding of how the universe evolves may be missing something fundamental, and we need new physics to resolve it. To settle this cosmic debate, new and independent methods of measuring the Hubble constant are highly sought after, which gets us to the story, Andrew.
Yes. We had to fill in all the blanks.
That's right. And so, as the article goes on, gravitational waves offer an entirely independent way to measure the expansion of the universe. And we know about gravitational waves. That's very much the stock in trade of what we talk about on Space Nuts. And so what they've done is gone back to one that was particularly interesting. And as you know, gravitational waves get their number from the date when they're discovered. This was GW 170817, so discovered on the 17th of August, 2017. That's only 2 years after the first one was found, actually. I think it's only a year after, I think. It's 2 years, certainly 2 years after the first one was observed. This was a neutron star collision, 2 neutron stars, and that has the property, unlike a black hole neutron star collision or a black hole collision, a neutron star collision actually produces radiation, electromagnetic radiation. It produces a flash or a glow. And that is something you can detect. So for a start, that means you know where these gravitational waves have come from with a high level of certainty. You can test all kinds of things like the fact that gravitational waves travel at the speed of light. All of that sort of pops out of GW 170817. So it was a remarkable event. What has now happened, though, is that people have used the analysis of that signal to sort of tease out the information about the Hubble constant. And they get an answer that is not as accurate as either of the other ones because they haven't got that precision yet for this method. But it's intriguingly like the measurement from the distant universe. That is the higher, the lower value. That's remember the distant universe measurements have about 67 to 68 kilometers per second per megaparsec. The other one was more like 73. This new value is somewhere between 61 and 70 kilometers per second per megaparsec, which kind of is outside the range of the near universe value. So it agrees much more with the distant universe value, even though GW 170817 came from a galaxy that is not that far away in cosmic terms. It's about 140 million light years from Earth, and that's sort of on our doorstep in galactic terms. So here you've got an independent method that gives an answer more like the distant method did, but it's using nearby objects rather than distant objects. So I think what it's done is very neatly thrown the cat among the pigeons again.
Sure has.
Well, let me just read the article. The last paragraph is, our result is still 4 times less precise than the leading nearby universe measurements. We will need to detect more neutron star collisions to definitively settle the Hubble tension using gravitational waves. Such events are rare, so it may be a while, but for now our study provides an important new clue in one of astronomy's biggest problems. And that's where they leave it.
Where does that place the story we did a couple of years ago about a study into the Hubble tension, trying to understand the differentiation between the two existing methods, where they said, look, the difference is not that big a deal. They're both right. So where does that stand now? Do you remember talking about that?
Yeah, I do remember. Yeah, we've covered it, certainly covered it before. Well, so if that's the case, if they're both right, and I think that was the outcome of that, then that's pushing you towards new physics, because to get 2 different results for the same thing by 2 different methods, both of which use general relativity as their basis. That is the firm basis of our understanding of the universe. What that suggests is there's something wrong with general relativity. Yeah. Now, we've believed that for a long time, but so far, all the tests, it comes out on top. It comes out with these incredibly precise accuracy in describing the way the universe works.
All right. Watch this space, I suppose, is where
indeed.
We're at on that. More to come. It's one of those issues that just won't go away because, being human beings, we want to figure everything out. So they won't give up on this. You can read about it at the Conversation website, or you can read the paper, which was published in the Astrophysical Journal. This is Space Nuts. Andrew Dunkley with Professor Fred Watson.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth.
Space Nuts.
Now, we got a question about the Large Hadron Collider recently. They were asking about the speed of 2 particles hitting each other at the speed of light. Would that be twice the speed of light? And the answer was no. But the Large Hadron Collider is in the news for a different reason. They're shutting it down. It's bye-bye Large Hadron Collider, but not forever. In fact, they're going to do some renovations. They're going to put a cubby house on top of it and a kid's playground.
Granny flat.
A little coffee shop next door. Probably not.
It's already got the coffee shop.
Already got the coffee shop. Okay. They're going to do a bigger coffee shop. That's really what this story is about.
Yeah. And the great thing from my point of view is that in just over 3 weeks I'll be there.
Wow.
I
love the line in this story on theuniversetoday.com. See you later, accelerator.
Yes.
I think that's very clever.
It's a nice one, isn't it?
Wish I'd thought of it.
Yeah, I do too. Actually, you've always got to be careful, especially when you write about this machine, because Marnie, in one of our earlier tours when we visited the Large Hadron Collider, had a spelling mistake in the word hadron, which you probably don't need to think too hard about to work out what it was, but somebody had to point it out.
Oh.
Is that what it really meant?
Transpose 2 letters?
Yes, you transpose 2 letters.
Yeah.
So
that would have got some laughs.
I think it did, yes. I think it did. I'm sure it's happened before, but Marnie never made that mistake again. But yes, we're going again. And the fact that it switched off actually makes us hope that we might once again get a trip down into the tunnel where the accelerator is, that 27-kilometer long circle of pipe work where the subatomic particles are accelerated, but also perhaps into one of the experimental caverns. The last one we were at was the compact muon solenoid. This is this machine that's as big as a small factory in a giant chamber underground, and it's called the compact muon solenoid. I love that. It's definitely not compact by our standards, but it was a fantastic thing to see. We're hoping we might see that again, but we'll see. So, yeah, we're nothing to do with the Large Hadron Collider. We're just cheerleaders to bring people to cheer it on, because one day we hope this machine might tell us what dark matter is, and that's actually what this upgrade's about. So what's happening? It's switched off at the moment. I think it is now switched off. See you later, accelerator. It's due to reopen in 2030, which will be a new version. It's called the High Luminosity LHC, Large Hadron Collider, and it's got 10 times the luminosity of the original machine. And I think by luminosity, what particle physicists mean is the number of particles that you can sort of charge around the circuit, the 27-kilometer ring that the particles charge around, being accelerated and focused by superconducting magnets. And I think that's what's actually being, upgraded. Yeah. So I don't think the speed will be faster. And if I remember rightly, these protons are accelerated to 99.99998% of the speed of light. I think that's the accurate thing. So that'll be probably the same speed, but many, many more particles. And that gives you a much better chance of seeing some of the things that we've missed. We've missed by the current version of the LHC, which, of course, is a triumph already. And in fact, on the day we're recording, today, 2nd of July, yesterday was the 14th anniversary of the discovery of the Higgs boson, which was done at the Large Hadron Collider. Wow. So a bit of an anniversary there.
That's gone fast, hasn't it?
Hasn't it gone fast? Yeah. And gosh, I think we've been talking about it that long as well.
Literally and figuratively.
Yeah, that's right. That's right. So, and of course, and this ties into our previous story. What we're all hoping for is that the new analysis, which will result from the high luminosity LHC, will give us insights into everything, but perhaps in particular the Higgs boson, and maybe will point the way, as the conversation piece says, will point the way to physics beyond the standard model, perhaps including evidence for supersymmetry or the existence of exotic dark matter particles. And of course, along the way, we hope they'll solve the Hubble tension as well.
Well, yes, let's hope so.
Yeah.
Yeah, it's so how long does this work take, you reckon?
I think it's going to take
quite some time.
Yeah, most of the time between now and 2030 when it comes back on. So,
wow.
Yeah, I mean, it sounds as though it is going to involve replacing all the superconducting magnets all the way around the 27-kilometer ring. And that's quite a thing.
The good news is if you want a superconducting magnet, there'll be some for sale on the side of the road in a few years' time, probably.
Yeah. I beg your pardon, I quoted it as being from the conversation, the article I was reading from, but it's actually Universe Today. So,
Universe Today.
By Alan Boyle.
Very good. All right. We'll watch with interest and hopefully an upgraded cafe as well, which will bring the tourists in big time for sure. I think that brings us to the end of the show. Fred, thank you so much.
They go so quickly, don't they?
They do. Yes.
Quickly. But I'll see you next time, I hope.
I hope so too. I couldn't do this without you, Fred.
I don't think I could do it without you either.
Well, at least you'd be able to talk about something. I'd sit here and go,
No, you wouldn't. No, you wouldn't. No, you can talk.
I can talk gibberish. I can do that a lot.
The term, the hind leg off a donkey. That's the term.
I could do that. Yeah, I could talk the leg off an iron pot. That's another one.
I like that.
Yeah. All right. Thanks, Fred. We'll see you soon.
Sounds great. Thanks, Andrew.
Professor Fred Watson, astronomer at large. Don't forget to visit our website between episodes. You can do that. And maybe if you've got time, wherever you listen to us, leave a review. Reviews are very helpful because they tell people what you think of us, and that might inspire them to listen. It might not, depending on what you say. But yeah, reviews are very, very good if you can spend a couple of minutes doing that from wherever you listen to us. YouTube, Apple Podcasts, Spreaker. There's a whole bunch that we're on. And thanks to Hugh in the studio, who couldn't be with us today because he's dealing with a dark matter. And from me, Andrew Dunkley, thanks for your company. We'll see you in the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.